Okay, to complete this problem, we want to discuss or calculate the settlement for the building on piles. And as we noted, the building on piles has this pressure bulb, which only is in the silt. We transfer the load past the clay. There's the clay layer. The whole purpose, in a lot of ways, for the piles is to transfer the load past the clay that can be soft and just load the silt and see if that gives us a better result for the settlement. So for this problem, there's no basement, so the building load is 12 million pounds, and so to calculate the Q, it's very simple. It's 12 million over 60 squared. We've already established the point of interest is here. The ZF is this distance right there. So the ZF is the 97 minus the 34, which is 63. And that gives us a ZF over B of 63 over 60, 1.05. We're evaluating again the corner. So for the corner, we have to do our little trick to use the ZF over B of 1.05 over 2, which is 0.525, and then when we get the value, we're going to divide by 4. In this case, again, we have single drainage, so HDR equals H, and the H is what? H is this distance right here, from the bottom of the pressure bulb to the top of the silt. It's 114. And we've been given our, in the silt, our OCR is 1.11, so we get our, we'll use that 1.11 to get the sigma prime P. So in this case, we only need to make a silt table, because only the silt is loaded. And we have our T's, 0 minus, 0 plus, 10 and infinity. We get our capital T's. We're going to use the C sub V, which is 226. So 226 times the 10 years divided by our HDR squared. So C sub VT over HDR squared. We get a capital T of 0.17. And so we got our T, and this is infinity, and T equals infinity, so we have our capital T's. Our UXS at T equals 0 plus, we use the pressure bulb to get the UXS at T equals 0 plus. So, let's see if I thought I... So, remember, we're at ZF over B of 0.525, and we use our little trick, so it's below the center. The silt point of interest, I'm right in there, so I'm between 0.6 and 0.7 for my contour. And I used 0.67, it's approximate, I divided by 4, because that's our trick. We got to divide by 4 to get the corner. And we multiply by our Q is 3333. We get our UXS at T equals 0 plus of 558. Then we use our pore pressure curves. It's single drainage to get the factor, and it's single drainage, so we go into our chart here, because remember, for the single drainage portion, we cross off that. This becomes the middle of the clay, or the silt rather, and if we look, we have our capital T is 0.17, so we're going to go to capital T equals 0.17, and So this is capital T equals 0.1, this is capital T equals 0.2, so 0.17 is approximately there, and then we read off the value here, or we could read it down here, I guess it doesn't matter. So we get our we get 0.61, reading it off either the top or the bottom, and it's multiplied by the 558. We get 340. Again, the UXS is the key. Once we get our UXS, the rest of the problem is very simple. We get our U water table that you can all get. We add those together to get the U. And then once again, I look at the T equals 0 minus figure to get the sigma V. We take the sigma V minus the U to get the sigma V prime. That sigma V prime is going to be the same as that sigma V prime, because from T equals 0 minus to T equals 0 plus, the sigma V prime is the same. I add the 5158 to the 6424. I get 11,582. Then all of these are 11,582 because they're the same picture. And then I take these 11,582. Excuse me. I take these 11,582s minus those U's, and I get the sigma V primes. I use these values to create my chart. Notice my sigma prime P is what? We had an OCR of 1.11. There's my sigma V prime, 1.11 initial, or sigma V prime initial, so it's 1.11 times the 5158. Gives me the 5725 for my sigma prime P, which is the inflection point, so I get 5725 there. And we're going from 5158 to 5716, so I never make it to the sigma prime P. That means that we're only in this region for our epsilon V, so we use the C epsilon r in the silt, 0.08, and then we, at 10 years, we use the 5376. At infinity, we use the 5716. We get our epsilon V's, and there are epsilon V's. We multiply it times our H. Our H is 114. We get the delta H. Okay, so that's how we get the delta H for the, oops. So note, okay, let's look at the infinity one. So for our building on piles, we get 0.406. For our building with the basement, we have 0.384. So in this particular case, the basement works better than the piles. The settlement is a bit less. So in this particular case, you choose the, assuming the basement works, the basement is the one to use as a comparison. And it's a trial and error process. There's no shortcuts to all of this. So when you're in practice, you have to just work the problems and find out what the answers are. Okay, so I want you to work this problem. So this is exactly, it's different numbers, but basically the same problem we just worked. We have a building with a basement here, and what do I have? I've got a clay layer and a silt layer. And for the building on piles, we go past the clay, and we have the point of interest in the silt right there. So I want you to work this problem. And notice that, the building's 50 feet. The structural weight is 10 million pounds. And, oops, the soil, where are the soil properties here? Okay, let me, I thought they were on that page, but okay, so, to please use these soil properties, and what I want you to do is to do this calculation, and this is what you need to do. You need to fill in this table. So try to do this. This is for the building with a basement that has an upper compressible soil, which is in this particular case, it's the clay. We have the upper compressible soil is the clay. The lower compressible soil is the silt. So fill out this table. You can make your own at home, however you want to do it. But we've got depth at the point of interest, small t, big T, UXS, U water table, U, sigma V prime. Those are the headings. In this particular case, we're asking for the settlement at 15 years and infinity. So, your T's are going to be, you're going to get 15 and infinity here. And you need to get your ZFs, your ZF over Bs, etc. You got to get your Q. You have to do the ZF and ZF over B for the upper and lower. And then, we've done this a million times, but you can do the epsilon V calculations with our stress strain curves. Okay, so this is the table I want you to fill out. Do the best you can with it. Okay, so pause the video, fill out this table, go back to the video to look at the exact problem. Here's the problem. So you have to go back and forth a little bit, but in any event, do your best to do this. Okay, I'm going to assume that you have filled in this table, and this gets you started. I'm going to let you pause the video, check your numbers, and see how well you're doing for the upper part. You can work on the lower part here. I've given you a little bit of help there with the lower part. Check your numbers. So pause the video here, check your numbers, fill in the rest. Okay, I'm going to assume that you've paused it and finished. Then these are the answers for the building with the basement. Check your numbers with these. Pause the video and look at it. This is how you would use the pressure bulb chart. Oh, if I didn't mention, yeah. So, yeah. This is using the pore pressure curves. And these are the stress strain curves and how to come up with the final answers. at 15 years and infinity, we get these numbers. We have to add the Clay and the silt numbers to get the final. Clay and the silt numbers to get the finals. Okay, now we have the building on piles. Well, okay. I'm going to let you look at these numbers. Hopefully you work them yourself also for the building on piles. If you haven't worked them yourself, go back. You can create another table that only has one compressible soil on it. And you can work it the same way as this one. So check the numbers for this. This is like I say, it's the same problem. These are the pressure bulbs, the pore pressure curves, and the settlement calculation. And notice here are results, and in this particular case, the piles work better than the basement. The settlement is less. So sometimes the piles can be better, sometimes the basement can be better. You just have to do the numbers. To finish up our discussion of settlement, I just want to talk about one last thing, and that is something called secondary compression or creep. And this is the very last thing we will cover, and it's quite straightforward. And we have the last little bit of what we need to put it this way. What has been observed is that sometimes, under some situations, the settlement lasts longer than we predict with our theory looking at the excess pore pressures. In other words, our theory is that when the excess pore pressures dissipate, in other words, when the excess pore pressures dissipate and become zero, then all settlement should stop. And people noticed in some cases, not all, but in some cases, that the settlement still took place even after the excess pore pressures were zero. And to account for that, we come up with something called the secondary compression or creep. And I'm not going to go through this in detail, but most of this was done by observation. And we came up with a new soil parameter. The new soil parameter is C alpha, called the secondary compression coefficient. And I'm not going to go through the details of this. One of the main reasons I'm going through this is that sometimes this appears on the EIT exam, and it always appears in this form. In addition to, of course, in practice, you have to check this out. In a lot of cases, it's not that big, but there are some cases when this secondary compression can be significant. Most cases, it's pretty small. The equation used is S sub S is equal to C alpha times H over 1 plus EP times the log of T over TP. Okay, what does that mean? We're going to introduce time. TP is the time to the end of primary. What does that mean? The end of primary is a time that we're going to call when capital T approximately equals 1. A little bit arbitrary. We're going to call that the time at the end of primary. We talked about it before, and we noticed that when capital T was 1, that the excess pore pressures were pretty close to 0. So if we take that time as being the end of primary, which is a little bit arbitrary, like I say, because in theory, the end of primary is at time infinity. But in practice, people will take capital T as 1. And so small t is the end of primary. It corresponds to capital T equal to 1. We're going to call E sub p the void ratio at the end of primary. So the soil has a particular void ratio at that particular time. And so using our expression, put it this way, if we use capital T equals 1, then the end of primary time becomes simply HDR squared over C sub V. Okay, so the easiest way to use this equation is with an example. So here's the example. It says find the secondary compression at 20 years after the end of primary for this situation. So I've got my sand fill here, my clay, sand at the bottom, and I'm going to, given is the void ratio at the end of primary is 0.85, C alpha is given, and yeah, C sub v is given. So that's all the given, this is all the given information. Okay, what do we do? Well, we have to find T at the end of primary. Well, I'm going to use my expression HDR squared over C sub V. And when I plug in those values, I get time at the end of primary is 0.71 years. So I simply use this expression now and plug it in so that my C alpha is 0.02, my H is, now it's H, not HDR, notice. H is 10 feet because that's the thickness of my clay. And my end of primary is 0.85, so it's 1.85. And then the question asked for 20 years after end of primary, so I put in my 20 years at the end of primary, and we get simply multiply that all out, and we get the creep, or the secondary settlement, of 0.16 feet. So what do you do with that number to get a final settlement? You would add that on to the settlement that we've calculated normally, the rest of this, the previous that we've been doing. Okay, stop there.